What's going on? AP Calc, Mr. Ford here with another homework tutorial. This is for 6.1.3. Again, I'm recording these a little bit out of order, so I'm a little ahead of the game right now. We're going to be doing all of the problems here, although 634 is a review question from your pre-calc or Algebra 2 days, but it's going to have a little bit of an application and become a bit of a preview problem near the end, and I'll tell you exactly what's going on here too. So this is all about population growth in 634. According to the State Department of Finance, California's population was 33.218 million at the beginning of 1998, 33.765 million at the beginning of 1999, and 34.336 million at the beginning of the year 2000. Calculate the percent increase from 98 to 99 and the percent increase from 99 to 2000. All we really have to do here for question A is be dividing. The percent increase from 99 to 98, that's 33.765 divided by 33.218. We're just dividing the population in each year by the previous year. So let's bring calculator cam up. Oh, look, our exponential graphs from class. 33.765 divided by 33.218 is going to give us 1.0165 if we round up a little bit. And if we do the same thing with the next year, the growth from 2000 to 1999, we're going to do the same kind of problem. We'll do 34.336, and we'll divide that by 33.765. That was the change from 2000 to 1999, so 34.336 divided by 33.765, and we get, looks like about the same thing, 1.0169. I mean, with very small difference, we get pretty much the same answer there. So I would say that since these are about the same thing, I would say that yes, there does seem to be a consistent percentage growth. I think like that. So that would be kind of where I would go with this. In both cases, we're looking at about 1.6% growth. If you move the decimal point 2 spots to the right, 1.6% growth appears to be the case here. Now, question B, assuming exponential population growth, we want to write an equation to model this data. Here's where your pre-calc or maybe Algebra 2 comes into play. We do teach this in Algebra 1 also, but all we got to do here is write kind of an equation. How about y equals? We'll start there. Usually what you want is your initial growth. It kind of depends, by the way, of which year you're going to start with. But if you want to use, let's use the year 2000 since that's the last one that we have. So in the year 2000, there was 34.336 million. And we also know that the population was growing by a factor of 1.0169. So we're just going to multiply by 1.0169 to the x power. And that's all you really need to do there. There's your exponential growth model. Of course, if we want to answer the next question, question C, all we got to do here is plug in x equals 20. Now, I'm knowing that because I used the year 2000's data. So in this case, x is the number of years after the year 2000. If you use 99's or 98's data right here in this spot instead of the 2000 number, you'd have to adjust. But I'm going to use x equals 20. So all I really need to go is go on my calculator and do 34.336 times 1.0169 to the 20th power. It's going to be kind of a bulky calculation, but that's what it is. So 34.336 times, in parentheses, 1.0169, all raised to the 20th power. It looks like I can expect the population to be, I don't know, about 48 million people. That's a pretty reasonable thing. It's about 48 million. Looking at the published answer guide, they have about 47.8 million from their model, so we're about the same. It's going to change a little bit depending on what year you're choosing because that also affects which multiplier you're doing. So question D, here's where it gets to be a calculus question. The increase in population is proportional to the current population. In other words, if the population is growing by 3% each year and the current population is 1,000 people, the increase is 30 people. If the current population is 5,000 people and the increase is 150, according to our model, by approximately how many people did the population increase in the year 2000? I think what's important here is to recognize that we are just taking a consistent percentage of each previous population and finding what that is. So In this case, the proportional relationships are a constant times x. In this case, the constant would be the 0.03 that we're multiplying by for that 3% example that we have there. But let's see. In 2001, let's see. If we think about the year 2000, where there were 34.336 people, let's think about the year 2001. And 2001 is really easy to do because all I got to do is take 34.336, that's the population in the year 2000, and multiply it by 1.0169, which appears to be the growth factor that I got from the division up above. And the new population, according to my calculator, stand by. You can see my calculator down below. The new population is going to be 34.916. Now, if you subtract those numbers, 34.916 minus 34.336, 34.336, we get 0.58. Don't forget, though, that this is in the number of millions of people. So if you move the decimal point 2 spots to the right or something, the answer here is that there was a change of 580,000 people. So the question they're asking is how many people actually joined, like number of people, not percent growth. So from 2000 to 2001, we can expect 580,000 people or so to join the population. The next question ties it all together. Explain why the increase in population is proportional to the current population. Well, because we're just multiplying by 1.0169 each time. The percentage growth is actually the constant of proportionality. So this is y equals k times x. In this case, k is just the percent growth, 1.0169 in my case, like that. Again, you get a slightly different k depending on which 2 years you're comparing, but they mostly are the same. So you're just multiplying each year the current population by the percent growth, and that makes it a proportion, where you're just multiplying by something. Keep this proportion talk kind of in the back of your head because it's going to pop up later on in Chapter 7, especially looking at this kind of stuff. Okay, Chapter 635. We got a bunch of integrals here. We're going to consider the multiple tools available for integrating and use the best strategy for each. So here we go. Now you got to work backwards in question A. At this stage, I'm just going to pause for a minute. At this stage, these are both derivatives that we kind of know. I do know that the derivative of 6 to the x power is the natural log of 6 times 6 times 6 to the x, and we'll talk about that in class later on. I also know that the derivative of the derivative of secant, the d dx of secant, is the secant of x times the tangent of x. So we're going to use this information to think backwards about this first problem here. First of all, if you take the derivative of 6 to the x power, you do get natural log of 6 times 6 to the x power. So for our antiderivative, we want that 6 to the x to stay. But if I were to take the derivative of 6 to the x, we would need a way to cancel out the natural log of 6 that comes with it. So let's go ahead and put natural log of 6 on the bottom of that fraction. So that way, when you take the derivative of 6 to the x, the natural log of 6, which is just a number, it can cancel out with itself and leave just 6 to the x. We should also put minus 3 secant of x here, because the derivative of the secant will be the secant tangent. And we should also put plus c down, because that's the best way to handle that derivative. So we're just working backwards with these things here. For question B, we can actually do this by hand, so let's actually do this. It won't be too tough to do. We might need some space off to the side, though. We got a little bit of work to do on this problem. Pi is just a constant hanging out in front. We have the integral from 0 to 2. Let's go ahead and expand. We can't expand. This is 4x squared minus x to the 4th power. That's with respect to x dx, like that. Now, to actually do this, let's find the antiderivative. We'll leave pi alone. And the antiderivative here is going to be x to the 3rd over 3, and we'll have the 4 hanging out there like that. And the derivative of x to the 4th is x to the 5th over 5. So we will evaluate this integral from 2 to 0. The nice thing about that is that plugging in 0 doesn't do anything, so we don't really need to worry about plugging in 0. We just got to plug in 2. So let's call this pi times, very carefully, 4 times 8 over 3. 2 to the 3rd power is 8. Minus 32 over 5, like that. Now, that's not going to be a fun thing to do either. Well, it's 32 over 3 and 32 over 5, which makes you tempted to do something there, but you can't. So we have to convert to make the same denominator. 32 times 5 is be 160. This is 160 over 15. And 32 times 3 is 96, minus 96 over 15. And so 160 minus 96 is going to give us 64 pi over 15. That's the final answer I have for this problem. Bada bop bop boom. Not super cool, but also kind of doable. So question C, moving along. This is one that I don't... Let's see. I'm tempted to cancel out the x plus 5. I'm willing to bet that the top of this fraction factors nicely. In fact, I'm pretty sure that it does. I'm going to write this problem off to the side, and we'll do it over here. Let's start with the integral from 1 to 4. That's not a fun integral to deal with, but we can handle it. Let's think about the top of this fraction. Can we factor 3x squared plus 13x minus 10x? I'm just going to kind of think about this one for a minute here. Let's see. I know I would need a 3x in the front slot for both of the binomials. I need something that multiplies to 10 and then adds together with this multiplication to make 13. 5 and 2. 5 and 2 would do the trick. How about minus... No. How about plus 5 minus 2 like that? That'll work. Because then you'll get the 15x, positive 15 from the 3x times 5. And you'll get the minus 2 from negative 2 times x. That'll work. Okay, so let's go ahead and rewrite this right away. We'll have on the top of the fraction 3x minus 2. And on the bottom, times x plus 5. Oh, and that's nice because then the bottom cancels out, x plus 5. Which makes this a much easier integral to deal with, since the x plus 5s cancel out. So now we have the integral instead. We have the integral from 1 to 4 of just 3x minus 2, which is a much easier integral to evaluate. The antiderivative would be 3x squared over 2 minus 2x. We're going to evaluate that from 4 to 1. Plugging in 4 would give us 3 times 4 squared over 2 minus 2 times 4. That's the first chunk. Minus plugging in 1, which gives us 3 over 2 minus 2. Let's see, working through these steps here. 4 squared is 16. 16 divided by 2 is 8. 8 times 3 is 24. 24 minus 8. Minus, and this is just 1/2, negative 1/2 actually. So this becomes 16 plus 1/2. I like the answer of 16.5, don't you? 16.5? Yeah, that works. 16.5. Cool. And then question D is an indefinite integral, so all we got to do is find the antiderivative here. Let's start by taking let's write down the variable of m. Let's take the degree up 1, from negative 4/3 to negative 1/3. Of course, to cancel that out, we need to also divide by negative 1/3, which we're probably just going to write as a times negative 3, like that. That way, the derivative part will at least give us the negative 4/3 in the exponent. Of course, let's not forget that 6 is also here, 6 times that. So negative 18 m to the negative 1/3 is probably the best answer. Plus c, don't forget plus c there. Yeah. Okay, let's move on. Now we have some graph drawing questions. 636 asks us to sketch a continuous function that satisfies all of the following conditions. So some of these are limits of the derivative, not the function. And let's think about where is f non-differentiable. So we got to think about this one. There's probably a lot of different graphs that we can make for this, but let's think for a minute what this tells us. The limit as x approaches negative infinity of f of x approaches infinity, which means the graph approaches, let's see, if I'm thinking about this, actually, maybe we could start drawing a graph right away over here. Just going to kind of put down this. I know the graph kind of goes up and to the left like that. That's all that information tells us. That as x approaches negative infinity, the graph itself approaches positive infinity. So it goes up and to the left that way. The limit as x approaches 0 from the left of f prime of x, careful here, is negative 1. What that means is that the slope, f prime, let's think about that. As you approach 0 from the left, the derivative or the slope is negative 1. So right before 0, I'm going to go ahead and make kind of a diagonal line. In fact, I'm just going to make this whole thing like a diagonal line here with a slope of -1. Kind of a perfect 45-degree angle. We're looking for a slope of -1 there. I believe so far that takes care of the first two. Next, we have the limit as x approaches 0 from the right of the graph f prime is +1. Again, this is the slope as you approach 0 from the right. So it appears there's got to be a sharp corner here, because we got to have the opposite or a positive slope right there. M is equal to +1. I don't know what's going to happen beyond that, so I'm not going to write anything else there. I also know that as you approach infinity, positive infinity, it approaches 5. So there's got to be like a horizontal asymptote. You could do like up and then back down here and maybe like that. And let's just say that's y equals 5, something like that. I think that'll do it. Because of the non-converging limits on both sides at x equals 0, you're going to have a sharp corner right there. Remember, the whole idea with a derivative is that the limit as x approaches 0 from both sides is the same thing. And since they're not the same thing, that the derivative does not exist at x equals 0. So where is f non-differentiable? X equals 0. It's got a sharp corner there. Let's look at one of these flag problems. We haven't seen these in a while, but they're going to start being more relevant as we move into Chapter 8, which we hopefully have time to get to a little bit here. We have a flag shown at right. Imagine rotating the flag about its pole and describe the resulting three-dimensional figure. So if we were to kind of try to draw this, it would look kind of like a dog toy, I guess, is what I have in mind. I don't know if you can kind of see what I'm thinking about here. You'd have kind of this dome shape with a kind of a rod in the middle of it like that. And you would have another dome shape kind of like this. Be kind of a that's actually a really good drawing for it. Hey, thanks guys. That would be kind of what you got, like a dog chew toy maybe. As far as finding the volume of this, it's actually really simple to do, because these two halves actually make one sphere. So when you think about the volume here, there is going to be a sphere plus a cylinder. So the sphere part is relatively easy to deal with. The only thing we don't know about it is going to be, well, we do know its radius, because we know that this is 6 here, and so it's got to be 6 this way also. So that is a sphere with a radius of 6. Now, if you don't know the volume of a sphere, that's okay, because I'm going to go Google it, honestly, because I don't memorize it myself. On an AP question, they would tell you what the formula would be. The sphere is 4/3 pi r to the cubed. 4/3 pi times the radius cubed. Like that. The radius has to be 6. As far as the cylinder goes, that's also pretty easy, because the cylinder comes from this section right there, that little square being rotated around there. It gives you this little section down here. There, marked in red. And that has a height of 3 and a radius of 3 also. So the cylinder formula, which is the area of the base times the height, pi times the radius squared times the height, which in this case is both 3. So I suppose we could simplify this as much as we can. 4/3 pi times 36 plus, that's going to be 27 pi right there. And nicely enough, 36 divided by 3 is 12, and 12 times 4 is 48. So we have is 48 pi plus 27 pi, and that's just going to be a total of something, 48 plus 27. 75 pi, I believe, is the final volume for that shape right there. That's not what the book has. What did I do wrong? Oh, it's 6 to the 3rd power. Whoopsie, whoopsie. See, I made a little mistake there. I'm glad I checked it. 6 to the 3rd power is not that number. 6 to the 3rd power is a huge number. Hang on, I gotta think about it. 6 to the 3rd is 216, which does divide by the 3, by the way. It does divide to make 72, but 72 times 4 is 288 pi. There we go. Well, I'm glad I checked that really quick. 288 plus 27 is going to give us 315 pi. That's a better answer. There we go. Checked it. Got it. Okay, cool. Let's move on. Where are we? 19 minutes? Which is pretty good. 38, we got a bunch of functions with respect to given variables, and all we got to do is differentiate them. We got to find the derivatives. But we're not going to panic too much, because these are going to give us a chance to practice a lot of our basic derivative ideas here. The first one is incredibly easy if you have been paying attention to your logarithm rules. The idea here is that this is the same. This just equals x, because 2 and the log base 2 of x actually kind of just cancel out. And so the derivative dx of y equals just 1. The derivative of x is 1. Over here in question B, we have a little bit of a chain rule to do here. So at this stage, we kind of know how to do the derivative of any base to the x power. But we have to think about chain rule first. The derivative of tangent is the secant squared of the original inside. We're going to leave that alone. Secant squared of 10 to the x power. But then we're going to multiply by the derivative of the inside part, which is the natural log of 10 times 10 to the x. So that's all we need to do. We do not need to go any further with that. That's as simple as it's going to get. So there you go. Chain rule. The derivative of 10 to the x is natural log of 10 times 10 to the x. Over here in question C, we're looking for the derivative of the cosine times the tangent. This one is incredibly easy if you do. We saw this in the last homework too. If you just do a little bit of trig, it makes your life a lot easier, because the cosine times tangent can be easily written a little differently. Tangent is just the sine over the cosine, and so these guys cancel out, and so this is just the sine of x. So the derivative, dy dx, in this problem is just the cosine of x. Don't make that problem any harder than it has to be. You could use the product rule there, but do not do this. Here on question D, we have another chain rule, which is going to look very much like the previous problem. The only difference here is that instead of 10 to the x, we have a much easier derivative. This is the secant squared of e to the x times e to the x. There it is. Very common question on AP style tests also. And here we have 2 raised to the cosine of w to the third power. This one is going to be a real pain in the butt, and so I don't like it, but we're going to try it anyway. This is going to be a triple chain rule problem. The first, if you break down the functions going on here, the first outside function is 2 to the x power. But the x in this problem is actually cosine of something. And then the thing inside of the cosine is w to the third power. So we actually have, if we're doing the derivative with respect to w involved, we actually have 3 layers to peel down from this one. So this is actually, let me change this dy dw, since it's the variable in question. Let's start with the derivative of 2 to the x. It's the natural log of 2 times 2 to the x power. In this case, the x power is the cosine of w to the third. So there's the outside layer. We just did it, leaving the entire inside intact. Let's go to the second layer, the derivative of the cosine, which is negative sine of the inside, like that. And then finally, we have to peel out the layer that's the derivative of the inside of that, the derivative of w to the third power, which is 3w squared, like that. Now, you can clean this up considerably, I suppose. You can gather the negative. Let's put negative 3 natural log of 2 out in front. That's usually what you kind of see in these problems. Then you have your 2 times 2 cosine to the w to the third power times the sine of w to the third times w squared will be the last part of that answer. Excuse me, I gotta take a phone call really quick here. This is Mr. Ford. Totally, yeah. I'm recording a video, so she'll just come in, and I'll be talking to myself, so, yeah. Yeah. Bye. Okay, let's deal with a vertical motion problem here. I know we're at the 23-minute mark here, but we're going to keep going. I have been taking a lot of time to explain things, too. You guys are awesome. Thanks for keeping up with this. I know it's a lot of work here in March of your senior year. We have the acceleration due to gravity is a constant near the surface of the Earth. Its accepted values are as follows. We've seen these a million times in different physics classes. Negative 32 feet per second squared, or negative 9.8 meters per second squared, depending on which units you want to use. These values are all the information needed to derive the equations for any dropped or thrown object. See, here's the thing. You can easily find the velocity function when given the acceleration function in question A, because the velocity... Let's see, black pen, please. There we go. The velocity is just going to be the integral of the acceleration, or the antiderivative of that. Now, the antiderivative, let's say if we're using feet per second, we've seen this before, is going to be negative 32t plus c. Because if you take the antiderivative of 32, or sorry, negative 32, then you get negative 32t plus c. The quiz is on my standing desk back there if you want to grab a copy of it. Yep. Now the key here is the plus c. That's what's going to make every velocity function a little different, because every function has a different constant or a initial velocity going on there. Usually in these cases, the plus c, the c is what we call our initial velocity or a beginning. So in question B, write an equation for the velocity of an object whose initial velocity is 120 feet per second. That's incredibly easy to do. The velocity is negative 32t plus 120. All you got to do is plug the 120 in there. There's a little bit going on behind the scenes here. If you really wanted to solve that algebraically, you know that v of 0 is negative 32 times 0 plus c, which you also know is 120. So 120 equals c is a good way to also algebraically prove this exact same idea going on there. Question C, write an equation for the height of the starting position if the initial position of the object is 100 feet. This is also pretty simple. All you got to do is take the antiderivative of your velocity, which in this case is negative 16t squared plus 120t. And then, of course, you got to put another plus c on this thing. But we've seen this enough times. This is plus 100 because your initial velocity, or sorry, your initial height is going to be that thing right there. The mathematics is exactly the same here. We know, I'm going to use blue for this, we know that the height of t is equal to negative 16t squared plus 120t plus c. But we also know the h of 0, which is just going to be 0 plus c, we know that's equal to 100 because that was given to us. So that's another way of proving that the initial height has got to be 100. That's what your c is, like that. As far as questions D and E go, we'll use the calculator for a lot of this. What's the velocity of the object when it hits the ground? Well, we need to figure out when it hits the ground first. That's the first challenge of this problem for question D. We want to know when h of t equals 0. When does it hit the ground, in other words? So to do that, I honestly would use the calculator. That would probably be the best way. I'm going to do most of this right on that little device there. I'm going to go nice and slow through this process too, because I know calculator stuff can be kind of a pain. If you have Desmos, this is an even better tool, I think. And if you're doing this after the fact, watching this on a computer, hopefully you can open up a Desmos tab. But I'm going to go ahead and open this up. We got to know when the object hits the ground to begin with. We do not know when that happens. So I'm going to graph it. Before I do that, I'm going to change my window. I think it's probably going to happen in the first 10 seconds. And I don't really care about the max because all I really want to know is when it's going to hit the ground. But I do know that the initial position was 100, so I'm going to take y max up to like 200 or something like that, just so I can see everything there. So the graph's going to go way off the page there. Hopefully we can see the 0 happen. So yeah, we're interested in what that t value is right there. So we'll go into the calculator. We'll do the 0 function, and we'll do a left bound and right bound right around there. Left bound, right bound, and a guess. It's about 8.25, I guess, 7. 8.257. So this happens at 8.257, like that. Now what we want to know is what's the velocity at that time. We want to know what v of 8.257 is. And unfortunately, we've got a formula for that. We've got a function right up here. So we're just going to plug that right into it. I'm going to use my calculator. It's going to be negative 32 times 8.257 plus the initial velocity of 120, which it looks like negative 144 for this problem is what I'm getting at. Negative 144.22 feet per second. This is my answer for D. I'm trying to section off my work here for these problems. Like that. I don't know if that helps or not. As far as the maximum height attained by the object, again, we could do this in calculus by finding the velocity when the velocity equals 0. In this case, that's, I don't know. It's probably better to just use the graphing calculator, honestly. We got to take our y max up quite a bit more, though. I'm going to guess 500 here, because I do want to see the actual maximum of the graph. So maximum height, honestly, a calculator is the better tool for this job. If we want to know the maximum, let's just do the left bound and the right bound, and we'll do our guess right in the middle. Looks like the maximum is at 3.75, 325. We could have found that by setting the velocity equal to 0 to find the time and then plugging that time into the height function, but not interested in that. As far as at what time is the object's speed the greatest, that question, oof, you know, man, what time is the object's speed the greatest? I suppose that's probably best assumed as when the object hits the ground, which happens at 8.257 seconds. We actually already know that. I don't like this question very much for a lot of reasons. I feel like it's outside of the scope of this class because it involves a lot of guesswork. But remember that this is the height function right there. The velocity function, the problem here is that it's a straight line, negative 32x plus 120. It's always a straight line. And the problem is that in this case, let me change my window a little bit. We only care about the absolute value of the speed, which is really tough to gauge from the graph. I suppose if you want to talk about the maximum distance that this red line is ever away from the x-axis, it probably happens right there when the object hits the ground. So I'm going to say that the book agrees with me that this is when the object hits the ground at t equals 8.25 seconds, 8.257 seconds. I don't like this question though. F is kind of a it's a bad question for calc. It's a good question for physics, but it's a bad calculus question. And let's do 640. One more of these to look at here. If f is a continuous function, f prime of 2 is negative 1, f prime of 3 is 1. Must there be a function a in between 2 and 3 such that f prime of a is 0? Let's try it. Let's think about what this is saying. So we have 2 and we have 3 on our graph. We know that it's a continuous function, and we know that the slope of that line when x is 2 is negative 1. So maybe I'm just going to put like a little diagonal 45-degree angle line right there that represents the slope of negative 1. I don't know what the function is doing, but I do know that its slope at x equals 2 is negative 1. I also know that the slope at 3 is positive 1. So I don't know where that happens up and down, but I do know that it has to be positive 1. So I'm just going to put another line like that. And keep in mind that either of these diagonal lines could be pushed up and down anywhere you want. We don't know where they happen. We just know that the slope is negative 1 and the slope is positive 1. The question is, must there be a spot where the derivative equals 0? Now, we do know it's a continuous function, so it's really easy to say yes to this because here's an example that does work. You can have your graph come down like this, have that tangent line there, and then have it turn around and start increasing like this. That would give you your tangent lines. Let me make them a little more pronounced. That would give you your tangent lines that you're looking for with the appropriate slopes. However, nothing is said in this graph about this f being differentiable. So we should consider the case that you actually, instead of having this line, what if we had a cusp there? What if our graph came down like this and then bounced off and went like that? That would mean at no point is the slope 0 in this range. So it's not. The answer here is no. There could be a cusp. So, all right, 33 minutes is a little long for a video, but you know, we did have a lot to talk about there, and I do like a lot of these problems. I think looking back on it, I'm probably not going to assign the first question. I think I'm glad it's in this video, but I'm not going to assign 34 in the final draft of this, because I'd rather have you guys focus on things that are actually relevant. 37 is probably optional too, the more I think about it. So I'll probably, in the final draft, that's what I'll probably say, and I'll probably honestly omit 639F as well. So there is that. Okay, anyway, have a great time. You guys are awesome. Thanks for making it this far in the video. I'll see you in the next one.